let's go ahead and write down the fundamental theorem of calculus fully here. The fundamental theorem of calculus, FTC for short, being a theorem, it's a statement with an if clause and a then clause, hypotheses or premises that come after the if, and a conclusion that comes after the then. The idea of a theorem, when you want to apply a theorem, is if the hypotheses are satisfied, if they're true in a certain example, you know from the truth of the theorem that the conclusion follows. The hypotheses are these. If little f is continuous on a closed interval from a to b, so that we have interval notation, and capital F is an antiderivative of little f, capital F has the property that its derivative, capital F prime of x, always equals little f of x for all x in the interval. You might say, how could that include the endpoints? Well, one way is you could imagine the domain is actually a little bit bigger than this closed interval on which these derivatives are equal. Otherwise, at the left and right endpoints, you can actually define what are called one-sided derivatives, but we won't have to worry about details here. Typically, these functions will be defined continuous and differentiable on bigger intervals. Then the conclusion is to evaluate the definite integral of little f of x with respect to x. All you have to do is plug a and b into capital F and do a subtraction and simplify. Capital F of b minus capital F of a gives you the value of the integral. Again, this is amazing. It should feel like magic. Does that mean it is magic? No, it's not magic. It just feels that way. Why in the world should this work? I want to get to a point very soon here today where we feel like it's somewhat intuitive, actually. You can evaluate the integral, the area under the curve, or the signed area between the curve and the horizontal axis if it goes below the axis, where you count areas above the curve when it's below the axis, negatively toward the integral. You can find those areas by subtracting antiderivative values. That again is that realization is truly the start of calculus. That's what Newton and Leibniz discovered. They didn't really have full rigorous proofs like we do today, but they had arguments for why it worked, and they had examples, and they used it to do some pretty amazing things. Newton, for example, in describing the motion of the planets around the sun. Why do the planets move in ellipses around the sun? And there's a couple other of Kepler's laws. Why do those work? Kepler didn't know. Kepler lived before Newton. He didn't know why the planets move the way they do. Newton used calculus to prove why the planets move the way they do, assuming that his laws of motion hold, like Newton's second law, F equals ma. Applied to the planetary system, the solar system, in vector form. You have to think about vectors as well. So it's a little bit more complicated than I'm letting on here, but this is the heart of what he did. And he used it for other things too. It is something that's always true because it's a theorem, it's been proved. It is very often quite helpful to evaluate integrals, but there are situations, like I mentioned last time, where it's actually not helpful. That doesn't mean it's not true. It's still true. It's just not helpful. What are those situations where it's not helpful? We will encounter them, maybe today, for sure next Monday, when finding capital F is either too hard or maybe even, you might say, impossible. That's when it's not helpful. It's still true, but it's just not helpful because you don't have a formula for capital F. Because there are plenty of functions, hundreds of functions out there that you've never heard of before. Essentially, you can use integrals to define new functions Though to approximate those functions with technology, for example, you have to use the integral. You have to approximate the integral with sums, left and right hand sums and their averages, and more advanced things, something called Simpson's rule, ultimately. We are not going to prove the fundamental theorem of calculus. One proof of it does use the mean value theorem. Remember, the mean value theorem is also thought of as the most valuable theorem. The mean value theorem can be used to prove the fundamental theorem of calculus. There are other proofs that don't use the mean value theorem. But we do want to understand its meaning and interpret it in context. Now, we've talked about physics. We've talked about, what if f of t, say, is velocity? Last time the emphasis was that the integral of the velocity was the change in position. Hey, change in, we've got a minus sign there. Yeah, it's a change in the function value. That kind of idea applies more broadly. I also mentioned the tank filling situation. Let's imagine that again. Pretend this is a tank. We've got water flowing in and we got water flowing out. Maybe you even have a certain amount of water in there to start with. There's a faucet up here and a drain down here. As I said before, the net flow rate is the inflow rate minus the outflow rate. And this applies not just to tanks with water, but it applies to more general situations. Maybe the water is not an amount of water, but it's like a population of, I don't know, rabbits in Minnesota. The tank is Minnesota and the water's rabbits. And you got an inflow rate of rabbits coming from Wisconsin and Iowa and South Dakota and North Dakota and Canada. And you got an outflow rates leaving Minnesota. Of course, it's not quite this like the schematic, right? They could run into each other. The rabbits could be waving at each other as they cross borders. But this idea still works. It doesn't have to be rabbits. It can be people moving in and out of the state. The net flow rate, you could call it a net inflow rate, is the inflow rate minus the outflow rate. If the inflow rate is higher than the outflow rate, then the net migration is inward. And if the outflow rate is higher than the inflow rate, then the net inflow migration is negative. This can be positive or negative. We can represent this as a function. I mean, you can represent each of these as functions. I could do that. I could call this one g of t and this one h of t if I like. And the result I could call f of t. Switching variable name from x to t. It's okay. T represents time. If I'm imagining it to be water, typical units here might be in liters per minute or milliliters per second or whatever you want to say. We've got a graph of the net inflow rate, f of t. Maybe sometimes it's positive, sometimes it's negative. Maybe it starts out positive, then goes negative, then goes positive, then goes negative again. And at the end, it's positive. Maybe that's your interval. Let's say A is here at 0 and B is some number up here. You could pretend it's whatever you want, maybe 20. This would be a t-axis in minutes. This would be a what? A flow rate axis. What should I call it? Maybe R for rate. This would be in liters per minute. The integral from A to B should be interpreted as the total change in volume in liters. If we integrate from A to B, this what I'm about to say is super duper important. This is the kind of perspective you want to have when you're sitting in your science class and your teacher writes an integral on the board and says, oh yeah, this quantity is obviously equal to this integral. And you're like, huh? Why? It's because they're thinking about it in this kind of way. Not this exact same example necessarily, but similar kind of thinking. Could write f of t dt here. That again is the flow rate, the net flow rate in liters per minute. What you imagine dt to be here in this context is you imagine it to be a small amount of time. How small? Well, really, really, really small. What's that? 1 second? 1 millisecond? Technically much, much smaller. It's infinitesimal. It's smaller than any number you can imagine or even measure. Maybe I should have said that the other way, that you can measure or even imagine. Do such numbers exist? No, they don't. Not in the standard real number system. That just implies there's a non-standard real number system, perhaps, in which they do. But non-standard analysis is way too difficult. Okay? It's graduate level math. And I've looked at non-standard analysis books. So here's my experience with a non-standard analysis book. I picked one off the shelf in the library. I looked at the first page and I'm like, huh, and I put it back. It was too much for me. Okay? It's very, very, very advanced. You can make infinitesimals rigorous. It's just very, very, very difficult to do so. Most people would say not worthwhile. Some people have said, yes, I think it is worthwhile. I think it's too difficult for me to spend time on when I've got other things to do. But I do still like thinking about it intuitively. We can still think about it intuitively as a convenient fiction. And I can't emphasize enough how helpful that is for science classes. That's the way scientists think about it all the time. That's what they're doing when they say, yeah, obviously this got to be this integral. Imagine this is an infinitesimal amount of time. Infinitesimal. See if I can spell it right. Infinitesimal, infinitesimal amount of time. I mean, the units need to be the same. This would be in minutes. Just for the sake of concreteness, you could imagine it to be not a millisecond, I guess, but a milliminute. What would that be? Would that be 1,000th or 1,000,000th of a minute? I forget milli. That 1,000th? Or maybe a microminute, 1,000,000th of a minute. Okay? You do want the units to be consistent. And you imagine f of t dt as a product. Is it a product? No, but pretend. And if it is a product, then its unit should be liters per minute times minutes. Cancel the minutes, liters. F of t dt, well, should I give it a symbol? How about in this example, at least, dv for what? Change in volume. That's what. For this example, this wouldn't work for other examples. It wouldn't work for rabbits migrating in and out of Minnesota. You'd want to call it dp, perhaps, for change in population, if it was rabbits or people. I'm calling it dv to emphasize that for this example, I'm thinking of it as a change in volume. Tiny change in volume. I could say infinitesimal change. Change in volume. It's just about the notation is just meant to be suggestive. Okay. We typically use V for volume. So dV represents a tiny change in volume. Infinitesimal small amount of change in volume. As a product of this quantity, f of t, which is not infinitesimal, right? F of t is not infinitesimal. At any given value of t, it's got some definite positive or negative value. Could be 0 at some values of t, but only finitely many of them. That's not infinitesimal. That is, a regular number times an infinitesimal number is an infinitesimal number. Okay? Convenient fictions. What about the integral sign? Does that change the units? No, because the integral is just like adding. That's what the way Leibniz thought of this, and that's why he used an elongated s. He was thinking sum, I guess in German. Leibniz was German. I don't know what the word for sum is in German. Must start with an S, but I'm not sure. I took German in high school, I should know, but I don't. The Gates. Okay. Sum. Add up the little infinitesimal changes in volume. Well, you know, if you add up the little infinitesimal changes in volume, what else are you going to get but the total change in volume? Done. The integral is obvious. The fundamental theorem of calculus becomes obvious. I'll say it again. Listen really carefully. If you add up the tiny infinitesimal changes in volume, I should probably use changes, tiny infinitesimal changes in volume, what else could you possibly get except the total change in volume? It's true by definition. This is going to be the total change in volume. I can't spell the word change today for some reason. Change in volume. Symbolically, I can't spell the word volume. I'm too excited. Symbolically, you could write delta V instead of dV, right? You see in your science textbooks, sometimes they write delta, sometimes they write D. It's like, what in the world's going on? Here, at least, I can't speak for science authors. Here, at least, dV is a tiny change in volume, infinitesimal change in volume over an infinitesimal amount of time elapsed. Delta V is not infinitesimal. It's an ordinary number amount of change of volume, though it could be positive or it could be negative. Sum up the little changes in volumes, you get the total change in volumes. That's the fundamental theorem of calculus. Well, wait a minute, where's the capital F? Well, it's hidden in this. This is capital F of B minus capital F of A, where capital F of T is the volume at time t for the tank. If there's water in the tank to begin with at the start at t equals 0, then F of 0 is positive. If water's flowing in faster than it's flowing out, I mean, you don't have to turn off the faucet when you open the drain. You could have the faucet on, water flowing while the drain's open. Water could be flowing in faster than it's flowing out when the flow rate is positive. When it's negative, then it's flowing out faster than it's flowing in. If water's flowing in faster than it's flowing out, then the volume is going to go higher. Delta V will be positive. If the water's flowing out faster than it's flowing in, then the volume is going to go down. Delta V will be negative. Over some bigger interval of time here, the final answer could be positive, it could be negative. In fact, I've drawn it in such a way it's kind of hard to tell. This area would be, let's just pretend this is t equals, what would be about right there, maybe 7. The integral from 0 to 7 would be positive because the graph's above the axis. Let's go ahead and give it a value. Let's say the area is, just to make something up here, 10. What would the units be? Units of liter, multiply the units on the axes, liters per minute times minutes. This would be in liters. Yes, you've never measured area in liters before, but that's what the interpretation of the area would be for the application. Continue from time 7 to time, say 12. Now it looks more like 11. 11, this area contributes negatively to the integral. Now I could label the area as a positive area as I did last time, but realize when it helps us compute the integral, it contributes negatively. I'm going to pretend it's 6 liters, but its contribution to the integral is -6 because the graph's below the axis. This area, I'm going to pretend is 2 liters, and that's contributing positively to the integral because it's above the axis. The water level is going up from time 0 to time 7. At time 7, it starts going down again from time 7 to time 11. Then it starts going up again a little bit from time 11 to time, say, 14. before going down again from time 14 to time 20, and then up again from time, well, this is time 19, say, up again from time 19 to time 20. What should I pretend this area is? I'm just going to try to eyeball it, compare it with that. It looks like it's a little smaller than that one. I'm going to call this 9 liters. And this one I'm going to call somewhat similar to this. I'll call it 2 liters. Maybe it's more like 1.5, but humor me. So the final value of the integral is going to be 10 minus 6 plus 2 minus 9 plus 2. 4 plus 2 is 6. Minus 9 is negative 15. Oh, no. 6. Sorry. I was thinking negative 6 minus 9. 6 minus 9 is negative 3. Plus 2 is negative 1. How about that? I ended up with a negative value. I could say the integral from 0 to 10 of f of t here. Here's something I could do. Not that you have to do what I'm about to do, but you can do it. I could break this integral up into a bunch of pieces. The integral from 0 to 7, plus the integral from 7 to 11, plus the integral from 11 to 14. I'm picking the numbers where the function f of t equals 0, plus the integral from 14 to 19, plus the integral from 19 to 20. Yes, thank you. That should be a 20 over here. This is a 10. The area was 6 up here for that one. But again, it contributes negatively to the integral. So I have to subtract 6 or add negative 6 if you prefer. Then I added 2, then I subtracted 9, then I added 2 again. Negative 1, right? Double check that. Does that look good? 4, 6, negative 3, 2, negative 1 liters. In other words, by time 20 minutes, you have 1 liter less in the tank than what you started with. This is the change in volume. It's capital F of 20 minus capital F of 0, where capital F of t is the volume at time t. This is so important. It's important that you know the area interpretation of integration. It's important that you know this property. It might seem like, why would I bother writing all those integrals? Well, usually you wouldn't. But I do want you to know it's true that you can do this. You can break up the interval from 0 to 20 into a bunch of, well, consecutive subintervals, 0 to 7, 7 to 11, 11 to 14, 14 to 19, and 19 to 20. And I can integrate over each piece and add the results. That's called a interval property of integration. I will write it down in abstract form here in a few minutes. But perhaps most important is to realize that this is the way you want to think of it. It's like I'm adding up the tiny volumes to get the total change in volume. And yes, you can think of that as a difference of capital F, where capital F, the volume at time t, is an antiderivative of little f. I haven't mentioned that. That's important. Capital F of t is the volume at time t in liters. What's its rate of change? Its derivative. It's got to be the flow rate. The units are certainly right. I call this v here. dv dt, rate of change of volume with respect to time, is capital F prime of t. That is little f of t. Its units are for sure liters per minute for one thing, and it should make sense that, yeah, I mean, the rate of change of the volume with respect to time should be the net flow rate. That should just make sense. Am I proving that? Not really, but it should make good intuitive scientific sense that the rate of change of volume is the flow rate. That's really what flow rate is. It's a definition of flow rate. So it is an antiderivative, confirming the truth of the fundamental theorem of calculus here at a gut level. And it really is almost obvious. Again, because the integral of dv gives total change in v. I should have the f of t in. Okay, no. When I say integral of dv, dv includes f of t. It's the f of t dt thing here. That's confusing as well, right? You see those in science textbooks as well. Hey, that kind of makes good sense as well if you think of the Leibniz notation for the derivative as being a fraction. dv dt equals f of t, quote unquote, multiply both sides by dt, and what do you get? dv is f of t dt. Hey, that's what I'm integrating. That's what I call dv there. Kind of feels like we're going in circles here, right? Like around and around we go. Maybe each step feels understandable, but then when you kind of put it all together, it's like, what did we talk about here? It's not easy. Okay, if you don't get it, you're not alone. It takes a long time for this to really sink in. You got to think about it consistently. Do you have a question? The Leibniz notation is both confusing and helpful. It's technically not a fraction, but we're treating it like a fraction. The fact that we're treating it like a fraction is confusing, but at the same time helpful once you get used to it. This applies more generally. In fact, the FTC is sometimes redescribed as the total change theorem. Once again, the total change theorem should be an if-then statement, should have hypotheses and a conclusion. The hypotheses of the total change theorem are stated a little differently than the FTC. I'll go ahead and write it. Suppose little f is a differentiable function on the interval from a to b. I was debating in my mind right before I wrote that whether I should use a little f or a capital F here. I could use either symbol. Decided to go with the little f. You don't see the word if here. I could have made it an if. If f is differentiable on the interval from a to b. Then what is the conclusion? The conclusion is the total change in little f, delta little f, which by definition would be little f of b minus little f of a, is the integral of its rate of change. It is the integral of its derivative. Went back to using x here, I could have used t. To find the change in a function over some interval from a to b, there's the change by definition. You integrate its rate of change. F prime of x dx, you could think of as little changes in x. You could call these df's if you like. A little weird, but people do it. That's the other thing, is you got to get used to weirdness and inconsistent notation. It's like, oh, all these different authors use all these different notations that are inconsistent. I mean, I could have also said y equals f of x and called that dy instead of df. Maybe that would have been less confusing. I could have done that. To find the total change in the function, add up the little changes. From an intuitive standpoint, it's obviously true. To find the total distance I walk, add up the little distances. Each millisecond I walk a little ways. Sometimes I'm walking faster than other times, so sometimes those small distances over each millisecond get bigger or smaller, but they're still small. I'm not going to walk very far over a millisecond. Add up all those little distances, I get the total distance traveled.